Assalamualaikum, myself Tayyaba Akbar, registration number 21TE65. This is our lab number 8.
This lab, what we have to do, first task is we have to define the filter. A filter is basically it is a context of digital signal processing that refers to the system or algorithm that modifies the characteristic of the digital signal, and they are used to enhance and suppress the specific components of the signal. And there are two types there are some types of filter. First is low pass, second is high pass, third is band pass. Low pass allow the frequency below the specific cutoff frequency, and it is used for removing the high frequency component. And high frequency allow the frequency above a specified cutoff, and band pass passes a specific range of frequencies. And the band stop filter, basically it attenuates a specific range of frequency while allowing the frequency outside the notch to pass through. It is also used to remove the interference or unwanted frequency components. Okay, the next one is what are the time domain parameters for a filter. So there are two parameters, step response and the overshoot. We are going to discuss the good and bad impacts of both of these. A good step response indicates that the filter settle quickly and smoothly, and the bad step response, a poor step response, exhibit and show the settling time, excessive overshoot and undershoot, like that. Now comes to the overshoot. A low or negligible overshoot is desirable, and it indicates that the filter output is matching to the desired response or not. And bad overshoot, excessive a bad overshoot is excessive overshoot can lead to the signal distortion and ringing and all that. Next one is linear phase. We are going to discuss its good and bad impact also. So the first one is a linear phase is considered beneficial as it ensures that all the frequency components of the input signal experience the same phase shift, and they preserve the signal waveform and avoid the phase distortion. And this is particularly important in the application where the phase coherence and the signal fidelity are critical. Now the next is non-linear phase response, such as the phase distortion or the phase shifts that vary with the frequency can lead to the signal degradation and smearing of the transient signal and all that. And the non-linear phase can introduce the distortion that affects the intelligibility and the quality of the signal. And the last one is what are the frequency domain parameter for the filter. First is roll off, second is ripple in the passband, third is poor stop band attenuation. Roll off, a good roll off refers to the rate at which the filter frequency response decreases from the pass band to the stop band. And ripple in the pass band, a good filter has minimal or negligible ripples in the pass band. And the poor stop band attenuation, good stop band attenuation refers to the filter ability to effectively suppress the frequencies outside the desired pass band, ensuring the unwanted signal are eliminated. Now here, first of all, we have defined our signal. The first task is we have our MATLAB function, and what we did, we have x is equals to zeros and the range that is given to us is 1 to 40, and then we have used the figure command and subplot and given the title x and y labels also. Then we have to compute the Fourier transform of the signal. For that we have taken x is equal to FFT. FFT is used for the Fourier transform. Then we have to use the magnitude response. So we have used the abstract function here, and now we have to plot the amplitude response in the frequency domain. So again we have used the subplot and the titles x and y labels, both of them. At last we have to use the signal in the frequency domain, so we have did the same thing for that also. And here is the output for this function. Okay, moving on towards our second source code, that in this function all the things are same. We have used the same code as we have used in the previous task, but one thing that is different, that is the range of the function. Here the range is different and all the code is same to this task. Here the range is different and all the all the code is same as the previous one. So moving on towards the output of this system. So this is the output of this function, and the first one is the signal in the time domain, second is magnitude response, and third is the
signal in the magnitude domain.
Based on the 121 and 161, this is our next one, and here what we did, we just have changed our value of x here, and the desired output, the given output is this one. Moving on towards the next task, here what we did, first of all we have used the value of the x, and then we have defined our function, and the value of the range is from 1 to 161, and after that we have used the signal command, and we have add the noise, then we have defined the moving average filter, and same as the above we have used the subplot, and for plotting the filtered signal in the time domain we have used the subplot, the plot command, the title, the x label and the y label, and after that we have used the Fourier transform FFT function, and here it is the output. The first is the filtered signal in the time domain, then magnitude response of the filtered signal, then filter signal in the frequency domain. The next lab task we have given, we have to apply the 11 tap symmetrical around the moving average filter on the signal x noise and observe the time and frequency domain. Here what we have to do, we have to make the filters they have used x is equal to 0 is all this command that we use in the previous code. In the next lab task, only one thing that is different is we have 25 tabs, so we have to use the same code as we have used the above, but the number of tabs is changed. Moving on towards the next lab task. In the next lab task, what we have to do, we have to see from this example number 7.2, in which we have given the 7 tab filter, 17, 51 and 101 filter. Moving on towards the code, this is the code, and in this code the n is representing the number of tab. We have given the sampling frequency, that is 8000, and the cutoff frequency, that is 800. Then we have to display the signal, and for that we have used the subplot and title command and x and y labels, and then we have to use the transfer function because we have to display the signal in the symmetrical form, so we have used the transfer function. Then we have used figure command for plotting our graph, x and y labels to show what we have to represent on x and y, and title, and after that we have to drive the points, and here we have used the frequency. So our output is this, we have our signal. In the next task, the one thing that is different is the number of tab. Here we have to use the number of tab, that is 51, so we just have to change that, and this one is the output. In the next lab task, what we have to do, we have to apply the filters that are made in the signal x signal, and then we have to observe the changes that in that signal in the time and the frequency domain while varying the number of the coefficients of that filter. So in this lab task, what we did, first of all, we have given our sampling frequency and the time domain, and there are the 3 signals that are given. We have to add all of the 3 signals, and we have to convert our original signal from frequency domain, and we have to plot it. Basically here we have the number of the filters that are 50. We have to apply the FIR filters, and for that we have used the carrier frequency, and again x label, y label, subplot and plot command, and this is our output.